All right, welcome back. So in the previous lecture, we talked about the physical interpretation of the photon number states and squeeze states and so on. So let's try to address some practical issues, which I think people have tried, and I think there is some relation to what we have understood. So I try to explain that. You might have heard about gravity waves. Okay, so Einstein in 1916, I think he predicted the existence of gravity waves. When he developed the theory of relativity, these waves are predicted to exist. But nobody really measured them. Even electromagnetic waves are relatively easy to measure. Heinrich Hertz did it in 1880s. So gravity waves were predicted, and for a long time this was something of a holy grail. People spent large amounts of money on that to understand and verify. It's some sort of a validation of a theory. Okay, to predict something that was nearly a century back, and if you can observe it, it's amazing, right? So one of the predictions of the gravity waves was that if you have an object, let's say a spear, or maybe a spear, something like this, a spear, and if you subject it to a gravity wave, over time, it very, very slightly stretches and compresses. Okay, even the spear, we think that, what is there? If I put a spear, why should it change? But when there is a gravity wave, there is a slight elongation and compression. Okay, and that is what I'm trying to represent in the left picture here. So here you think of, time axis is going down, and the periodicity is, let's say, tau g, the time period of a gravity wave. So you think of a circle, a spear, and then when the gravity wave passes through, it stretches in one dimension and it compresses in the other dimension. Effectively, the spear will become an ellipse. Now, as the wave passes through in time, the time period of a gravity wave can be something, okay? When that happens, you'll see that after half a time period, it stretches in the opposite direction and then compresses in the opposite. So basically, the ellipse is basically stretching and compressing. Effectively, the circle is becoming an ellipse. The axis of the ellipse is changing with gravity wave. And this sort of gravity waves can occur when there are some cosmological events like a supernova, or cosmological events which have high energy and all that. That can actually cause these gravity waves to go through the space. Okay. Now, people wanted to measure them. Okay. When they wanted to measure them, I think some of the optimistic versions of the theory predicted that the delta L by L, if I take my length of my object, okay, in this case the diameter could be L, let's say, if the diameter was L, the stretching and compressing, right, that if I call it as delta L, that is, this ratio was optimistically estimated to be about 10 power 21. Sorry, not 10 power 21, 10 power minus 21. Okay, that means it's less than an attometer. An attometer is 10 power minus 18. I don't even know what is 10 power minus 21. Okay, so less than an attometer. So this is a very, very tiny fluctuation. And we still want to understand. Because you see, you might say, it's a illogical pursuit, it's a waste of money. But somebody bothered to measure the charge of an electron at some point. Now we take 1.6 into 10 power minus 19 or 1.602. Some of us might even know more number of decimals. But somebody bothered to measure that, millican. And that laid a lot of foundation to the rest of the science. At the point of millican, you might say, why should you care? I mean, that it's getting attracted. People knew, you just can rub, flannel and something else, two objects, and you'll have surface charges. Why do you have to quantify what is the minimum surface charge? Minimum charge that can be produced. Somebody thought about it and did that, and that had a lot of implications. Similarly, somebody wants to measure what is this change in dimensions. Okay. And this is not an easy task. You see, it's a very, very small change in the length. Okay. It's not a very trivial task, and people have built what is known as a LIGO experiment. Okay. It was in the news a few years back. So essentially, LIGO stands for Laser Interferometer and Gravitational Wave Observatory or something like that. So people wanted to observe the gravity waves, and they wanted to introduce laser interferometers. Why should we use interferometers? Interferometers is some of the most sensitive detection systems that we can have. So what an interferometer is, that you have a laser that is incident on a beam splitter, let's say. You split it into two beams. Okay. And they go and hit a mirror. This mirror is mounted on a spear, a suspended spear. And then you have this and two mirrors. So they go and hit the mirror and come back. And then they'll interfere and produce an output. Suppose there's a phase difference between the path. So now I'll call this an optical path. So the path length, right? So if there is a path difference, there's a small change in the path difference, either I'll have constructive or destructive interference. If the path difference is basically n times lambda, where n is an integer, then you have constructive interference. If it is n plus half, then it is destructive interference, and so on. Okay. The phenomena of interference which you might have studied, you would have studied about this. Now, this is a very sensitive thing that can be used, okay, to measure. So basically what I can do in this case is change in the path length. Produces a shift in the interference fringe pattern. Alright. So change in path length produces this. Now, by measuring how many fringes are shifting, we can calculate how much is a change in the path length. Okay. Now we said because of gravity waves, we have this mirror moving out and then mirror moving in, because these are two suspended mirrors in perpendicular directions. So basically when the sphere stretches in one direction, delta n will basically reduce. In the opposite direction, it should compress. We said that sphere becomes a ellipse, right? That's why we delta n, one is stretching, one is compressing. Okay. So now we want to measure this. Okay. If you want to measure this experiment is constructed with a laser. Let's say, a laser, typical number that I picked up from, actually this is from Mark Fox again. Okay. Okay. So the laser was 1.064 nanometers and the power was 300 watts. Okay. Now I want to measure this. So what will I do? How do I measure this? First of all, if I have this sort of a power, what is the number of photons? Because I want to find out what is the minimum uncertainty that is caused by short noise. Laser coherent beam. Okay. So what is a short noise? Phase delta phi that we can achieve here. Okay. The first, we know we have done this recipe multiple times, but let me go through it. If lambda is equal to 1.164 micrometers, your lambda in EV is going to be 1.24 divided by 1.064 micrometers. That will roughly translate to 1.17 EV, I believe. Okay, 1.17 EV. Okay, this is my energy of the photon. Now, if you have that energy of the photon, what is the flux? We have calculated it multiple times. Flux is basically power divided by energy in lambda, lambda in EV, right? So this is 300 watts divided by 1.17 EV. So charge 1.6 into 10 power minus 19. Okay. So we have this. So now what is the photon flux that you will have? If you calculate this, I have just written down on a sheet of paper here. So this is roughly going to be 1.6 into 10 power 21 photons per second. This is my flux. Okay. If I make a measurement in 1 second, roughly my average photon number is going to be equal to 1.6 into 10 power 21 photons. So what is the uncertainty in the number of photons now? Delta n is going to be square root of n bar. That is going to be equal to 1.6. So 4 into 10 power 10. Okay. Photons per second. Whatever. Photons, not per second. Okay. Now if I know this, what is the minimum, what is the limit? Short noise limit? See, short noise is basically your photons are coming. You're hitting, right? You're many shots of photons and there should be some fluctuations because the photon number is fluctuating. So there should be some noise. So that will be given by delta phi into delta n is going to be equal to half, right? So delta phi is going to be 1 by 2 delta n from the uncertainty, phase number uncertainty relation. So this is going to be 1 by 2 into, 1 by 8 into 10 power 10. Correct? Is it correct? So what should it be? 1 by 8 is going to be 1.25 into 10 power minus 11. Huh? 1 by 8 is 0.125 into 0.125 into 10 power 10. So 1.25 into 9, 10 power 9. Minus 9. Minus 10 becomes minus 9. Because 0.125 into 10 power minus 10. Minus 11, sorry. Yeah, minus 11, sorry. Yeah, minus 11. 10 power minus 11 radians. This is my uncertainty in the, sorry, not radians. Uncertainty in the phase. Now the question is, if this is my uncertainty that is there in the phase that we can have from the source, the phase change that is introduced by my delta L should be greater than that. So what I'll say is delta L by lambda. With respect to lambda, delta L is some shift that is introduced, right? Delta L is my change in this. That should be greater than, in this case, delta phi or delta phi divided by lambda corresponds to a phase shift of 2 pi. So my delta L now that we can measure with this is going to be how much? So delta L is going to be, delta phi is 1.25 into 10 power 11 minus 11 into divided by into lambda is 1.06 into 10 power minus 6 divided by 2 pi, which is 3.14. Okay, and 10 power 11, 10 power minus 6 divided by 3, so roughly it will turn out to be something in the range of 10 power minus 18 delta L. Okay, so what you see is, if you have an interferometer that you build out of this, the change in the length that I can detect, minimum change in the length I can detect is 10 power minus 18. But my theory tells me that, or my, I said optimistic estimates, that's the word Mark-Fox uses, so I just using that. So that tells me that delta L by L should be 10 power minus 21. So to achieve this limit, okay, short noise limit, short noise limited delta L is equal to 10 power minus 18 meters, right? That's my short noise limited delta L. So to get delta L by L of 10 power minus 21, I'll have to have this L to be in the range of kilometers. L should be kilometers. Okay. If you have L to be kilometers, then automatically delta L by L is going to be 10 power minus 21, roughly in that range that you can detect gravitational waves. Okay. And the beauty of this is somebody has done this. People have predicted in late 60s, early 60s, sometime they proposed this experiment. They called it LIGO experiment. For 50 years, they went on at it. Initially, the funding agencies would say, why do you want it? It's useless, that there's so much of iterations, politics and so on. Finally, NSF had funded it in multiple bursts. And I think it's hundreds of $1 million was probably given out to this. And there were hundreds of thousands of people working on this. And finally, in the year 2013, I believe, they actually discovered gravity waves. They confirmed the existence of gravity waves. And then for this work, 3 people were, Kip Thorne at Caltech was one of the guys, and he was awarded, he along with a couple of others were awarded a Nobel Prize in 2017. So it's almost like a 50-year work. Science sometimes, in this day and age, we think of science as something that immediately should benefit the humanity, otherwise science is useless. Okay? That is extremely narrow view of looking at science. Of course, that is important. Some of us should really work on that. But it is also important to equally work on fundamental aspects. It's not only about surviving till tomorrow or, till the next year. It's also about surviving till the next century or next millennium. And we are inheritors to a great legacy, and we should pass it forward, and personally believe that there is a lot of merit in fundamental science. Okay. So anyway, so 2015 Nobel Prize, huh? Oh, I see. The discovery was apparently in 15 and then Nobel Prize came in 17. See, but there was a lot of anticipation because this is one of the most eagerly awaited thing for almost a century. At the cost of a few $1 million, we are building that. At the risk of sounding political, we eat up more money in scams. So if you spend a few $1 million on some experiment which is validating some basic things, that's worth it. We waste way more than that in our scams. So, yeah, sorry, I should delete that. Okay. So, all right. So, this is the LIGO experiment. Now, the question is, what if you want to improve the sensitivity of this experiment? What can you do? See, all the derivation was done effectively assuming that the short noise limit is what is depending. Can I reduce my noise below the short noise limit? You cannot? Well, no. Sub-Poissonian, right? If you actually use sub-Poissonian light, you have below short noise. That means your sensitivity with to the measure whatever you're trying to measure is improved. So in fact, people have proposed this, and I just came across a paper with hundreds of authors maybe. So a lot of people are interested, and a lot of interesting things can be done, provided we understand the fundamentals. Okay. So this is, I hope I have convinced you that this is useful. I don't know, maybe I convinced you that it is not, it's beyond the reach of one person, but I think there are definitely aspects that can be done by individuals. All right. I'm optimistic about it. So now the question is, okay, fine. The squeeze states and all that, we understand conceptually, we are showing diagrams and drawing lines and all that. It's okay. But how do we detect them? Okay. One of the schemes for detecting is what we have already studied, some time back, when we talked about the photo detection and short noise below the, fluctuations below the short noise. We talked about Sub-Poissonian case, right? So I already talked about this balanced detector scheme that we introduced. So essentially that time I had suppressed the, local oscillator thing, but let's assume that, we can use what is called as homodyne detection. Okay. Homodyne detection schemes. Basically what we do is, if you have a small signal, it becomes difficult to detect that. So what we can do is, from the same source, we take a strong signal and also, have a signal which is weak. So the strong source, a strong signal, a strong input is called as a local oscillator here. This is local oscillator. This comes from the theory of electronics, local oscillator and then the signal coming in, and this sort of, detection schemes are routinely employed in the telecommunications. So now you have this local oscillator, which is a strong intensity beam, and then there is a signal which is coming with the same, frequency. So now they interfere. Okay. And you pass it through a beam splitter, put it on two different photodetectors, and then combine them both and then integrate it and measure the difference in the currents. So whatever short noise you have, that sort of reflects in the photocurrent. We have seen that, short noise current fluctuations are effectively equal to the average current, right? And there are some additional terms. Now the idea is, now how will you implement it? We already talked about this sort of a scheme wherein, you have two photodetectors which are balanced, and you bias them in such a way that the overall fluctuations in the classical fluctuations in the currents vanish between the detectors, and only you're left with the AC component, which is the short noise fluctuations, and that you couple and then measure as an output. So fluctuations in the current effectively capture the fluctuations in the intensity, right? That's a photodetector circuit. Now, what we can do is consider the case without a signal. Okay. No signal situation. What happens? Well, you have a local oscillator which is very, very strong signal, I said, and that gets split into two parts, and it falls on, it's a 50-50 beam splitter, so it equally falls on these two. Now, what will be the output? That we'll see. So I said, output is basically the currents are difference in the currents by photodetectors, but then because it's a 50-50 beam splitter, the average current should cancel out. Only the fluctuations remain. Okay. So fluctuations, if you look at fluctuations in the output, delta I output, this is proportional to basically local oscillator short noise. Every other form of fluctuations are taken out. Okay. So this is without the signal. Now if you introduce signal is basically a quantum source. This is classical, local oscillator is classical. It's a large number of photons. Okay, it can be treated classically. Classical source. Let's say signal is a quantum source. For example, a squeeze light, quantum light, I'll say. Okay, if I have squeeze light, I'll have to represent it, for a coherent state, I'll say x1 plus I, x2, and so on. I'll represent it by a complex number. Okay. Because remember, in the quadrature plot, you have x1 and x2 both are out of phase. So I can represent it as a complex number. So I'll represent that. Now I don't want to get into the theory of it and all that, but it can be shown that in this case, when you have a signal, delta I output is proportional to even the combination of signal and the local oscillator, can be, delta I output can be below short noise limit for at certain time instants. Why? Because at that point, let's say it's amplitude squeezed. You saw that the fluctuations in the fields are actually going in such a way that at some points the amplitude fluctuations are lower than the classical coherent source. Okay. So with that, if you are able to get below short noise limit, that means it's a quantum source, and we can actually find out what is the quadrature and so on. Okay. In a way, this is a phase sensitive detection scheme. At certain phase differences, you actually can look at the photocurrent output and determine. Okay. So we don't need to go into the theory, but this is a scheme that we can actually use to detect squeeze states. Okay. Any questions? We are not. Yeah. I mean, yeah.
This is also a method to determine supersonic.
Right.
So how do we differentiate supersonic and which squeeze state is?
If you have truly supersonic, what is it? Delta n is 0, right? So, I mean, it will show much below the short noise limit. It's a supersonic statistics. Yeah. It's an amplitude squeezed. But if it is a phase squeezed, what happens? Delta n is larger. Then the short noise limit will be not held. I mean, there are schemes to even measure phase squeezed. But let's not get into all the details. By the way, I'm sorry, I should have mentioned Mark Fox's textbook here. All of these slides are from Mark Fox. I mean, most of it, except where very explicitly mentioned. All right. Okay. Now, the last thing that I want to mention is the generation of squeeze states. Okay. So, I mean, we assume that they're just appearing out of thin air so far, but they don't. We'll have to generate them. And that involves area of optics, which is known as nonlinear optics. That's the most common way of doing it. So, wherein, initially when we studied optical materials, we said the polarization P of T is equal to epsilon chi and E in time domain, let's say. You have a certain amount of electric field, and then we said, there is a response. Of course, we said, okay, it's not instantaneous response, and then there is this, causality, and then we wrote, actually the frequency domain expression. P of omega is dependent on E of omega, right? We did that. But it turns out that this is an approximation. This is a linear optics approximation. Okay. It turns out that the more accurate description would be epsilon naught chi, I'll call it just, E of t, the first order susceptibility, plus epsilon naught chi of 2 E of t whole square, plus epsilon chi of 3 third order susceptibility, E of t whole cube, and so on. So basically, we have higher order terms that are coming into picture. Okay. This is higher order susceptibilities. I mentioned this probably when I talked about it in the lectures 2 or so, but we didn't really go into the details. But you have these higher order susceptibilities. It turns out that these are very small, so most of the time they can be ignored. But when you have large electric fields like those produced by pulse lasers, the susceptibilities can be significant, and actually they give you a lot of interesting effects, which are collectively known as nonlinear optics. There are a lot of interesting things. That's again another course in itself. Probably there is something on NPTEL on that. Anyway, so now let's think of a nonlinear crystal. What happens is, one of the phenomena that is used is what is known as difference frequency generation. So I can shoot a photon of, let's say, 2 omega. For example, I can shoot a green light. I can generate 2 photons of 1.06 microns. So from a high frequency light, I can generate 2 photons of lower frequencies. That's one of the down conversion we call it. Okay. Similarly, we can also have different processes which are called as parametric mixing processes. So in this case, what can happen is, if you have, let's say, one high energy photon, 2 omega photon, high energy, and I have a signal photon with a lower frequency, I can generate, it combines both of these input photons. For example, the 2 omega photon and the omega photon will combine in the nonlinear crystal and produce another photon, which is the difference. In general, it could also be that this is omega 1 and this is omega 2. So I can make it omega 2 equal to 2 omega minus omega 1. I can have this also. That's a more general description. But if you have idler and the signal to be equal, then we call it degenerate for mixing. And then, you can actually have a situation where the omega photon, in this case, okay, omega photon can actually draw energy from the pump and get amplified. Okay, this is what is called, it is actually a very common thing that we use in nonlinear optics. It's a way to generate various different frequencies from a single frequency. Okay, and there are a lot of interesting things that are required. Now, suppose if you don't have the signal photon at all, you have vacuum state that's ever present everywhere, right? So I have my pump, which is a very strong intensity. I have my pump vacuum photon. Now, what happens is at certain points in time, the vacuum will contribute some energy to it and generate an idler photon. So if you look at how the vacuum fluctuations are, it will turn out that if you have vacuum, we said that, it is basically, the circle, right? Centered around x1 equal to x2 equal to 0. So the intensity fluctuations in the vacuum will be flat, just constant everywhere. But now if you present, in the nonlinear crystal, you're drawing some of this energy from the vacuum fluctuations and generating an output. So in that case, you can actually squeeze vacuum. Is it amplitude squeezing or phase squeezing? Amplitude squeezing at some amplitude, because amplitude in the fluctuations, amplitude fluctuations are reducing, right? So at this point, you have reduced, or I call it squeezed amplitude. Right? So basically you can generate this squeezed vacuum. Okay. You can also generate squeeze signals and so on from here. It's not as simple as it sounds. There's a lot of interesting experiments that we can do, and then there's a lot of intense things that can be done. But it pushes the frontiers. All right. So this is how you can generate squeeze states. All right. So any questions? Well, we are not going into the theory, but I just wanted to give you an idea. I just mentioned this for the sake of completeness. All right. So with that, I'll stop this lecture. And in the next lecture, we'll talk about photon number states, and we will introduce some mathematical elements. And we'll go from there. Okay. So we are in the final stretches. So bear with me. Come to the end of it. Let's see. I think you will like it. Some of you will like it. All right. So once again, sorry for the interludes, but thank you so much for your attention. Bye.